Hey guys, this is Arshun John, and today we'll be looking at the Born Haber cycle. And for those of you who do not know, the Born Haber cycle is used to determine the experimental lattice enthalpies. This reminds me, I hope that you have really just memorized the key terminology mentioned earlier, because that will really help you memorize the order of the Born Haber cycle, and really how the Born Haber cycle works. I've come up with a useful mnemonic in order for you guys to really, in order to make it easier for you guys to understand the order of the Born Haber cycle. And yeah. So let me just erase this. Right. Alright, so the way I memorize the order for the Born Haber cycle is simply remembering abial. Now, if you've really memorized the key terminology mentioned earlier, this should be really easy for you to fill out. A stands for the energy of atomization. Forgive my untidy handwriting. So then we go on to B, which is the bond enthalpy. You have E, which is the ionization energy. E, which is the electron affinity. So I have included the definition for each of these keywords or key terms. I think you'll find it really helpful to memorize them. And L stands for the lattice enthalpy, which is what we are trying to find. Okay. Moving on to a sample question. Here we have the question to construct a Born Haber cycle for magnesium oxide. So this is a very typical IB question to ask. Generally, they would ask you for the equations to represent the lattice energy of magnesium oxide, and the equation to represent the electron affinities of oxygen. But in this instance, they're just asking us to construct a Born Haber cycle. So, what do we do here? Well, step one is to remember the helpful mnemonic that I gave you earlier. That is abial, and use this in order to construct your Born Haber cycle. So, what we do first is, remember, it is the first was A, so A here, and that's your enthalpy of atomization. Your enthalpy of atomization is going to be having an equation of mg. So this is how it starts off: mg s in the solid state, half O2, and G in the gaseous state. Now, the enthalpy of atomization causes the magnesium to move to the gaseous state and oxygen in the gaseous state. And this is approximately 148 kilojoules per mole. Then you have the bond enthalpy. The bond enthalpy, excuse me. See, I'm just following it. So we have finished A. Now we are moving on to B, the bond enthalpy. Bond enthalpy of oxygen. Well, if you remember the definitions, you'll know exactly how it relates to these equations. So it's half times 498. Then you move on to the ionization energy. The ionization energy, which is here, and the ionization of energy of magnesium will result in something like this. Now, normally you're supposed to include the states. You know what? I will include the states because I want to give you guys an accurate example. And well, so the ionization energy will have a value of 7, will be 738 plus 1451, your second ionization energy in this case. Then you move on to the electron affinity, which will, so this is the, I'm sorry if it's a bit untidy, but I hope you understand the general layout for the Born Haber cycle. So the electron affinity, you have the equation here, Mg2 plus O2 minus, and this will have the values finally. You will, so these are your values. Then you will have and this is where your lattice enthalpy goes. Remember, it's ABL. Remember it's ABL. So this is where your lattice enthalpy goes, where it's delta H lat MgO. This is what we're trying to find out. And we go down. This is where we start. This is where we started off again. And this is your delta HF, your delta. So your enthalpy of formation value goes here. In this case, it is minus 602. Forgive me, I didn't include this in the question. Generally, when they ask you to construct a Born Haber cycle, they will give you the enthalpy of formation. So in this case, it is negative 602. And yeah, so you just have to add everything subtracted by the lattice enthalpy, and that is supposed to give you the enthalpy of formation. So I realize this sounds quite confusing, so I'll actually do it with you. So let's start off. We start off with 148 plus 1/2, 498 plus 738 plus 1451 plus negative 141 plus 798 minus the lattice enthalpy, which is non-existent in this case because you're trying to find it. So it's minus x is going to equal to negative 602, which is your enthalpy of formation. So now we need to just add this up. Adding this up is going to be quite difficult, but we'll go on. 148 plus 1/2, 498 plus 738 plus 1451 plus negative 141 plus 798. 798 should give you 3,243. 3,243. Is that right? Yes. Minus x will give you negative 602, which means that x, or your lattice enthalpy, will give you, or will be, 2 plus 3243, which is 2641 kilojoules per mole, and that is your answer.